So the section 9.3 is actually split into 2 days. We have 9.3a today. You will have, please notice, a quiz next Tuesday. After your first day, after your long weekend, we will do a review before we do the quiz on the first 3 sections of the chapter. And then we will do 9.4 after that, and your test will be the week after that. Hey, yeah, we're going to do 9.3b a week from today because we're splitting into 2 sections. Okay. So today we're dealing with the complex plane. The complex plane is basically how you do complex numbers, a plus bi, right? Remember your complex numbers? A plus bi, okay? They're plotted as a coordinate, AB, where A is the real portion along the x-axis. The imaginary portion is now the y-axis. So you're just plotting the point out. That's how you graph them on the complex plane. It works like an x-y axis. So if I had to point out here, AB for A plus BI, this is the B, that's the A. The real portion of your complex value gets plotted on the x-axis. The complex one, the imaginary portion, goes on the y-axis. Just a coordinate system, just like regular coordinates. Okay. Now the modulus of a complex number is the distance from the origin to the point. Okay, remember absolute value means the distance from 0. So the modulus is the same number every single time. So in this case, with the example that I have here, the modulus is the distance out. To find the modulus, you essentially apply the Pythagorean theorem. It's the square root of a squared plus b squared. That's the modulus. How far away from the center it is. So far, pretty simple stuff, right? X, Y coordinate, only instead of X, you have the real portion, instead of Y, you have the imaginary portion of the number, and you have your distance from center. It works the same thing as R on the polar coordinates or anything along those lines. The modulus is the distance from center. How far away is it from the origin? Okay. So let's do a few examples. Plot each complex number and find its modulus. So 3 plus 2i. 1, 2, 3 on the real. 1, 2 on the imaginary. There's my point. I mean, really, come on. You guys ought to be able to do that without much of a problem. And then you want to find the modulus. Okay. Square root of 3 squared plus 2 squared. 3 squared is 9, 2 squared is 4, 9 plus 4 is 13. I have the square root of 13. Oh, don't worry. It will get more difficult. So, do B. Oh, come on. So the real portion, 4 root 3. Yeah, 4 point something. Well, you figure out, you got a calculator. Figure out what 4 root 3 is on your calculator. Oh. That will give you a fair estimate of approximately where you ought to put it.
7.
It's about 7.
Oh my God.
Yeah, because root 3 is 1.4. Yeah, I think it's 1.41 is root 3. I think it's something like that. 1.73. Boy, that's awful. So what do you end up getting for it? Yeah, it's approximately 7. So you go over approximately 7, 1, 2, 3, 4, 5, 6, 7, and then down 1, 2, 3, 4. So it would be there. And then your modulus is 4 root 3 squared plus negative 4 squared. Okay, 4 root 3 squared. 4 squared is 16. Root 3 squared is 3. 16 times 3 is 48. So this is 48. Plus 16 gives you 64. And the square root of 64 gives you 8. No, it's not plus or minus 8 because we're measuring distance. Measuring distance, it's always measured as a positive. How far away? Because remember, it's the absolute value of the distance. It's always listed as a positive number because it's how far away from the 0 it is. It doesn't matter the direction. We're not. If it was direction, then we have negative. We're not worried about direction here, just how far away it is. Okay, next one. Root 5i. Yeah, this is like having 0. What is my real value of this complex number? 0. I have 0 plus root 5i. So I go up a little bit more than 2. Square root of 4 is 2. Square root of 5 is a little more than 2. And what's my modulus? Square root of 5, because it's a straight line just that way. I don't have to worry about anything. If it's on the vertical, it's just how far it is on the vertical away from the origin. So in the next one, what's the imaginary portion of my number? 0, because I have plus 0i, which means I just go 1, 2, 3, 4, 5, 6, 7 in the negative direction. And my modulus in this would be 7. Remember, it's always positive. Piece of cake, right? But wait. Do I look like I'm joking?
You look like
That looks like okay, polar form. So what we are going to do is convert imaginary numbers in rectangular form, essentially, complex numbers, as polar numbers. Change them into polar form. And there will be reasons for this. Some seen today, some seen next time we do our notes. Okay. So, here's how it works. Yes. Therefore. Okay. So here's how it works. You don't, and I do think you do have all this down here, but here's what's going on. The angle I have, theta. R is the equivalent of my, oh my god, I was just blanking on it. Modulus, sorry, the modulus. R is the modulus. It's the distance from center. Okay? So, I have my complex number, my A plus BI. The cosine of this angle is the real portion over the modulus. And the sine of the angle is the imaginary portion over the modulus. That's what I have here. Multiply everything by R, both sides by R. I get R cosine is equal to A. So A is equal to this distance here is equal to R cosine theta. This distance here is equal to R sine theta. So A is equal to R cosine theta. B is equal to R sine theta. This is BI, so I have to have the I in there. And what do? We pull out the R. This is our polar coordinate. Where R in this case is the modulus. Yeah, that's the form. That's what we're looking for. So what do we have to do? We have to find the angle, and we have to find the modulus. That's what we have to do. This is very similar to taking regular coordinates, which we've already done, rectangular coordinates, and converting it over to polar coordinates. The only difference is that we have an I with our sign, because we did this with rectangular coordinates. If that was the point -4, 3, we've already done that. We did that with rectangular coordinates. Just now we have an I in there instead, so we have to have the imaginary portion included in our polar coordinate. Okay, so here's what we do. And you will need your calculators for this. Okay, you will need your calculators for this. Okay. So make sure you are in radian mode, not degree mode. Radian mode, not degree mode. So first thing we do when we do this, we want to have an idea of where we're at before we get too carried away. Where approximately, we don't need to be exact, which quadrant is our point in? -4, 3 is going to put us over here somewhere. Okay, so what we want is we need to figure out the distance from center, and we need to find that angle. That's what we're looking for. We're looking for that angle theta, and we're looking for r. R is the modulus. That's not a problem. We do that to find our r. R. So what's our r? 5. Yeah, 3, 4, 5. Now, here's the difficult part. We have to go back to where we're doing with the rectangular ones to find our theta. Can you find that spot on your unit circle? No, there is nothing that is going to work on your unit circle for that. This is why I said you need your calculator. Because in order to find theta, you need to do the inverse tangent of -3/4. -1. -0.64. I would put 0.644. Okay. We got a problem, don't we? That's not where our angle is. Okay. Shh. So what do we get? This angle here is actually down here. When I go to a negative, I'm going that way. That's not what I want. I actually want 180 degrees from that. I want the exact opposite that I'm going there. No, I don't subtract 180. And I'm not dealing with degrees, am I? What am I dealing with? Radians. What's 180 degrees? That would be pi, halfway around the circle. What I want to do is from here, go halfway around the circle. So I take this, my actual angle I'm looking for is pi plus that, or minus 0.644. And you get 2.498 is what I got. That's my angle theta. Yeah, it's kind of a pain because it doesn't work out exactly, but that's not a big deal. So our polar coordinates would be 5. Cosine of 2.498 plus I sine of 2.498. Yes, I know it's not like a pi over 3 or pi over 6 or some crap like that we've been doing. Life sometimes is messy. You've got to learn how to deal with messy stuff that doesn't end up exactly where you want it to be. Sometimes it's not, sometimes it's okay. The next one is actually easier. Where is this one located? Where's the point -3, -3? Right down here. First thing you got to do, find your R. Nine plus 9 is 18. The square root of 18 is 3√2. So there's our R. Theta is actually very easy to find on this particular problem. At what values do I have tangents equal to 1?
All the 4 values.
Yeah, the pi over 4s are either tangents of those are either 1 or -1. When I'm down here in this bottom corner and I've got a tangent of 1, that means, ooh,
5 pi.
I'm at 5 pi over 4. That's the one where I have a tangent of 1. So my theta on this one's actually really easy.
Yes.
So now I can come up with my number. I have my R, 3√2 times the cosine of 5 pi over 4 plus I sine of 5 pi over 4. And it's always plus when you put them, even though it might be minus in front, because when you take the sine and cosine of those values, what are you going to get? You're going to get negatives and positives according to where your angle is. So the negatives and positives for converting it back will take care of themselves.
So the only time it is inverse tangent, it's not that value theta.
Well, I'm still doing the inverse tangent is that this is a point that is on our unit circle. We can figure it out from that. First one is not a place on our unit circle, nowhere near a place on our unit circle. We had to use decimals instead.
Are we converting this?
No, at least not today. But they're not that hard to convert back though either, are they? You take for this last one, sine of pi over 4 is negative root 2 over 2. Sine and cosine is put negative root 2 over 2. Distribute the 3√2 times, root 2 over 2, and what do you end up getting? You end up getting -3 minus 3i. It's not that big a deal. Just do the sine and cosine, make them into numbers rather than sine and cosine of the angle, and then multiply by what's out in front, and you'll be fine. They're actually very easy to convert back. Okay, let's do the last one. First thing you do, sketch the point where it will be. Positive on the reals, negative on the imaginary. So positive, negative, it's going to be down there in that quadrant. Figure out R. R is actually really not that bad here. 4. Negative, because the square root of 5 squared is 5. Square root of 11 squared is 11. 5 plus 11 is 16. Square root of 16 is 4. Now comes the fun part. So that is definitely not anywhere to be found on your unit circle. So you got to bust out your calculator on that one. Take the inverse tangent. Of negative root 11 over root 5. Put it in parentheses. Yeah, put it in parentheses, put the parentheses around everything when you type it in. If you do that, if you want to have any problem, type it in just like what I have here, inverse tangent, parentheses, negative square root of 11 divided by square root of 5. And you should get negative 0.978. Now, that is actually a good angle for us. That actually is that angle there, moving in the negative direction, but there's a problem with that. We don't want negative angles. We want positive angles. Very easy to fix. Add 2 pi to that. Because 2 pi will take you around in the positive direction and give you a positive angle. So if you have a negative angle, that's an okay place. You want to convert it to a positive angle, you add 2 pi to that. So my angle is actually going to be 2 pi minus 0.978, which would give you 5.306. And then we just have to write it out. Oh, should be 4 out in front, not a 5. My God. My bad. Yes. Moves it around the circle and makes it positive instead of negative angle. That's all that does. Okay. Any other questions before we move on to the harder stuff? Actually, I think honestly this is probably the more difficult thing to have to do. The next part actually isn't nearly as bad, I don't think. Okay, you ready? Polar multiplication and division. So, 2 polar coordinates, z sub 1, z sub 2. If I want to multiply these 2 polar coordinates, it is you multiply the r's and add the angles. Multiply the r's and add the angles. So if you're doing multiplication, you multiply the real numbers out front, add the angles for the sine and cosine. Not a big deal, right? So division would be divide the r's out in front and subtract the angles for division. So if you're multiplying 2 coordinates or subtracting 2 coordinates, you're doing that. Now, why would you want to do this? Because remember, these are actually not polar coordinates per se. They are polar form of imaginary numbers, complex numbers. This is a way of multiplying, dividing complex values. Okay, it works the same way. You get a single complex number for an answer. Okay, this part already, yeah, this part's already filled up. Okay, so let's do this, because like I said, these aren't that hard. Now, there are two parts to this problem. Express the answer in polar and rectangular form. So first you want to do the multiplication in polar form. That gives you your polar answer. Then we will convert the polar into rectangular, and that's really easy to do. So 2 times 7 gives me 14. Cosine, and now I need to add the angle. So I need to add pi over 12 and 3 pi over 4. So I'm going to do that over here. 1/12 plus 3/4. Okay. So what's this in twelfths? This is 9/12, right? Which gives us 10/12, which reduces to 5/6. So I add them together, I get 5 pi over 6 plus I sine 5 pi over 6. There's one answer. Because remember, I want it in two forms. I want the original answer. There's part of it. Boom. Easy peasy, right? First part, walking apart. Add the two angles together. Now, to convert them to rectangular coordinates, from polar form to rectangular form. It's actually really easy. I have 14. What is the cosine of 5 pi over 6? Negative root 3 over 2. Plus, and then what is the sine of 5 pi over 6? Positive 1/2. So I have 1/2 I. The I goes from in front of the sign to after the number at this point. Trig functions always go at the end. When I have numbers, letters follow numbers. Now what do I need to do? Multiply through by 14. Negative 7 root 3 plus 7i. Easy. Easy. Compared to a lot of the crap we've done in here, that's actually pretty easy. Okay, give B a shot. Okay, remember you're subtracting angles on this. 5/18 minus 1/9 is 5/18 minus 2/18, which is 3/18, which reduces down to 1/6. So my angle is pi over 6. Square root of 20 divided by the square root of 5. 20 divided by 5 is 4, so I have root 4, which is 2. So I have 2 cosine of pi over 6 plus I sine of pi over 6. That's the polar coordinate. Divide the numbers, subtract the angles. Now, I have 2 times the cosine of pi over 6 is root 3 over 2 plus 1/2. I sine of pi over 6 is 1/2. Distribute the 2. I get root 3 plus I. Piece of cake. Questions? Okay. Convert to polar form and then multiply. So you could multiply the way they are, FOIL it out, take any I squareds, make them -1s, deal with all that crap, but you got radicals in there. You're going to have an absolute mess when you get done. It's just going to not be pretty no matter what you do. If you do it in polar form, it actually will look a little bit neater when you get finished. So the first thing we need to do is convert into polar form. So the first one, do it one point at a time. So for this one here, our R is the square root of 1 squared plus -1 squared, which gives me the square root of 2. So our R is the square root of 2. 1 root 2. Where's the point 1, -1? It's down here, right? And then if it goes out 1 and goes out 1 and goes down 1, right? What is our tangent of that? Our tangent's going to be 1 over 1, right? Which means it's another pi over 4. But we go around 1, 2, 3, 4, 5, 6, 7 pi over 4. So our angle would be 7 pi over 4. That's not that hard to figure out. So our first number is root 2 cosine of 7 pi over 4 plus I sine 7 pi over 4. And then we have to do the same thing for the other number, convert it over. So our R on this one, 2 root 3 squared plus -2 squared. 2 root 3 squared is 12. Right? Yeah. 2 squared is 4. 12 plus 4 is 16. Square root of 16 is 4. Oh, that's nice. We get up getting a nice even integer for that. There's our 4. Now we have to figure out our theta, and this is a little bit difficult, but this is one that is on a unit circle. I see the 2 and the -2. I can do that. It ends up being the same quadrant down here. 2 root 3 over, 2 down. Okay, so we've done some of these before. A reminder of how to do this one, figure it out. I have negative 2 over 2 root 3. Clear out the 2's. Negative 1 over root 3. Those almost look like points on our unit circle. Negative 1/2 and root 3 over 2 are points on our unit circle. What angle has the y value as negative 1/2 and the x value as root 3 over 2? Divided top and bottom by 2. What? Why would I do that? To make these look like coordinates on our unit circle. Y coordinate, x coordinate together. Where do I have a y here and an x there? What point has the x of root 3 over 2 and the y of 1/2? There's only one place where those are, where you have that. And that would be 11 pi over 6. So theta equals 11 pi over 6. So we have the cosine of 11 pi over 6 plus I sine of 11 pi over 6. And then we do our magic multiplication. What's 4 times root 2? 4 root 2. Right? Very easy. Cosine. Ooh, 7 pi over 4 plus 11 pi over 6. So 7/4 plus 11/6. Common denominator would be 12. Multiply these both by 3. 21 over 12. Multiply both these by 2. 22 over 12, which means that I have 43 pi over 12. Oh, dear Lord. Plus I sine of 43 pi over 12. Now, what is the last part of the question? It's not shown here, but it is on your notes. What is the last statement it says right up there? Leave the answer in bold form. You're welcome. Because would you want to try to... How could you convert this over? Yeah. What you would have to do is use decimals. No, it actually wouldn't be that hard because you'd have decimals. You could not be exact values. You would have to find the cosine and the sine on your calculator, 43 pi over 12. Take the cosine of that, take the sine of that, multiply those numbers by 4 root 2, and you'll get decimals, but you will have an answer. It won't be exact, but you will have an answer. Okay, questions?